So this lecture is about the linear regression models, which are non-linear in data. Remember, a regression model can also be non-linear in parameters, in which case you cannot use OLS, but you can use NLS, while models that are linear in parameters and non-linear in data, those are still called linear regression models, and those can be estimated using OLS, and this lecture will describe how to do that. So let's consider a very simple linear model which is non-linear in data. Like this one, yi is determined by some intercept, beta 2, xi2, and the last term will make it nonlinear in data. xi2, same x variable, but let's square it. xi2 squared. That makes it nonlinear in data. It's still linear in parameters. So this model claims that if the explanatory variables are exogenous, then the expected value of y given my x is equal to this quadratic function plus, sorry, I forgot beta 2, beta 2x plus beta 3x squared. So we're simply claiming that once I know x, the expected value of y depends on x according to this quadratic function. Remember, that allows a couple of different relationships between the expected value and x. It could look like this: expected value y given x and x, but it could also look like this. And note, it will also have the linear model as a special case. So it also allows the relationship between the expected value of y given x to be a linear function, because beta 3 equal to 0 is a special case. So if beta 3 is equal to 0 in this model, it simplifies to a model which is linear in data as well. So the question is simple then. How do we estimate these parameters if my model is non-linear in data? And the answer is very simple. You just create a new variable that is equal to xi2 squared. So what you do is create a new variable, and we then call it naturally xi3, the next variable in our sequence, and it's just simply equal to the square of xi2. Because once we have done that, our model transforms into a linear regression model which is linear in data as well. Now yi is beta 1 plus beta 2 xi2 plus beta 3 xi3 plus epsilon I, and there are no nonlinearities. So I can just simply estimate these parameters using OLS. Let's see this in practice. So here I have just some simple data, and I have allowed Excel to estimate the parameters in this model. It has estimated beta 1 to 7.7, beta 2 to minus 2.6, and beta 3 to 1.07. So all I need to do is, let's rename this to x2. I just have to create a new variable here. Actually, before I do that, Excel unfortunately doesn't update this equation. So let me freeze these y values so they don't update. So I go to copy and then just paste the values like this, and then just recalculate this equation. So we need to create a new variable. Let's do it in between here. x3, and it's just simply going to be the square of x2. So a2 squared. Copy this down, and now the final thing I need to do is just run OLS on where I explain y with x2 and x3. So let's do that here. Linest my y's and my x's. 1, ignore the statistics in this case, and we can see that we got the same result as Excel did, fitting a quadratic function to this data. So we see that as long as the model is linear in parameters, we can always use this same idea. No matter what the model looks like, if it's, let's say, beta 1 plus beta 2 e to the xi2 plus log of xi, sorry I forgot the beta 3, log of xi2, and so on. We just simply define this as a new variable, xi3, and then we define this as a new variable, xi4. And then we run a linear regression model yi on xi3 and xi4. Now this particular model right here, where we've added xi2 square, is very common. And the idea is that if I start with just this linear model, linear in data, but I suspect that there is some non-linearities between y and x, but I'm not really sure about what it looks like, then it's very common to tack on this xi2 squared variable, because it will capture some of the non-linearities. What you then can do is you can test this hypothesis, beta 3 equal to 0. And if you reject that hypothesis, it means that this xi2 square should be included and that you have some nonlinearity in between y and the x variable. If you cannot reject this hypothesis, then you may want to exclude and remove this quadratic term. You can actually go further here. If you reject this null hypothesis and claim that you should have an xi2 squared term, you might also want to try a higher order polynomial and include an xi2 raised to the 3 term. This model can capture more nonlinear behavior than the model where we only have the square term, and you can test if that is significant as well. You always have to weigh the benefits of including polynomial terms like this to the cost, and the cost is that you are introducing more multicollinearity in the model, simply because xi2 squared and xi2 are typically correlated. Also, you include more variables in the regression, more parameters to estimate, and that will make it more difficult for OLS. You will typically get a higher standard error if you include more variables. So here is one of the absolutely main points of this lecture. If you have a model which is linear in parameters but nonlinear in data, then you can just simply create new variables and transform this model into a linear regression model which is also linear in data. So that takes care of the estimation part. Let's move on to the interpretation part. So let's consider this model again, beta 1 plus beta 2 xi2 plus beta 3 xi3 squared plus epsilon I. We know that in a linear regression model, which is also linear in data, then we have learned that beta 2 is the conditional expectation of yi given xi, the derivative of that with respect to. Actually, we don't need the i's to do this interpretation, with respect to x2. The conditional expectation of y given all the x variables, take the derivative of that with respect to x2 and you have beta 2. This is no longer true. If you have a model which is non-linear in data, you cannot use this interpretation. Beta 2 is no longer the marginal effect of x2, if we call this the marginal effect. And we can see that quite easily because in this model, the expected value of y given x is beta 1 plus beta 2 x2 plus beta 3, missed this one, there should be a 2 here of course, plus beta 3 x2 squared. That's the conditional expectation. And if I take the partial derivative here, which is just an ordinary derivative because I have only one x variable, so we can write it like this also, makes no difference. The x will then be, this goes away, the derivative of beta 2 x2 is beta 2, but we also have x2 here. And the derivative of x2 squared is 2 times x2. So we also get 2 times beta 3 times x2. So as you can see, beta 2 is no longer equal to the marginal effect of x2. Instead, the marginal effect of x2 is determined by this expression. And this is a general result. Whenever you have a model which is non-linear in data, if you want to find this marginal effect, and that's typically the one that we're interested in, then you have to do this derivative yourself. There is one more important point to note here, and that is that the marginal effect depends on x2. It is no longer a constant. And that makes sense if you think about it like this. What we're doing here is we're modeling the expected value of y given x as a function of x, and we're claiming that this is a quadratic function, so it could look something like that. Then clearly the derivative of this, the slope of this, will be different for different x values. So how much the expected value of y increases when x increases by 1 unit depends on x. It depends on where we start from. Since we have estimates of these beta parameters, it means that we can estimate the marginal effect. And this is just estimated using, and then we just replace the betas that we do not know with the b's that we do know. b2 plus 2 b3 times x2. This is how we estimate the marginal effect. So let's just summarize these notes about the interpretation. So what we're used to from the model, which was linear in both parameters and data, this result, that's not going to be true anymore in general. If you're uncertain about how the relationship between the x variable and the y variable looks, then a common starting point is to add the square of the x variable, because that will capture some of the nonlinear effects. Another important nonlinearity to consider is the interactive terms. We'll get to that a little bit later. So here is the example that we've been considering. We believe that there is a nonlinear relationship between x and y, so we've added the square of x to our model as well. This is easy to estimate. All we have to do is just create a new variable, xi3, which is the square of xi2, and then we have a model that we can estimate using OLS, which will be just a simple linear regression model, which is also linear in data. For this particular simple model, we can find the marginal effect of x2, the marginal effect of x2, which is defined as the derivative of y given x with respect to x2, and it comes out to be this expression, beta 2 plus 2 beta 3 times x2. We just get that from differentiating the first expression and by removing the error term. And we note that this is actually a function of x2 now. It depends on the value of x2. We estimate the marginal effect by replacing beta 2 with b2. Let's consider a concrete example using Gretel. So let's say that I want to regress and explain final with only the math score now, SATM. But I suspect that there is a nonlinear relationship between them, so I want to add the square of SATM as well to my regression. So what you do then is you can go to Model, Ordinary Least Squares. You need to create a new variable, which is supposed to be SATM squared. And you can do that using this plus sign here. And just type the name of it, SATM, let's call it SATM2. And it's SATM raised to 2. Now you can run your regression by putting final as your dependent variable, including both SATM and the square of SATM. OK. And in this case, we got this result. We notice that the p-value for SATM is very high. So that means that the inclusion of this square of SATM was not a good idea. Actually, also by including this variable, the standard error of the SATM variable has increased a lot, making it insignificant actually. So this was definitely not a good idea to include it. Even so, if you want to figure out the marginal effect of SATM, that is, if you want to figure out how much you can expect the result on the final exam to increase if you increase SATM by 1 unit, then what you need to do is you need to take this number here, that's my B2, add to that 2 times this number, which is B3, and finally multiply that by a level of SATM. Remember, if you have an SATM score of 80, that will give you a different marginal effect now compared to if you have an SATM score of, let's say, 100. The effect of increasing SATM by 1 unit will be different depending on where you start. In eViews, you can just do quick estimate equation, type final C SATM, and you actually don't even have to create a new variable. You can just type SATM squared like this, and it will add the square of this variable to the regression. OK, and that gives you the same result. If you do want to create a new variable, which is useful sometimes if you use this variable a lot, you can do that by going to quick, create, let's see, generate series. And then you can create a new series like SATM2 equal to SATM raised to 2. Then you will have that, and you can use SATM2 as your new variable. So there's another type of nonlinearity in the explanatory variables that's very important that we need to discuss, and that is the interaction term. So let's begin with a linear regression model, which is linear in data as well as parameters, like this, and then we have an error term here. Now, an interaction term is simply a product of the two of the explanatory variables. I have only two in this case, I can only create one interaction variable, but I do it by multiplying these two together, and I create that as a new variable. So I add beta 4 and the product of these two. Again, it's very simple to estimate. All I need to do is to create a new variable that I call xi4, and that will just create a linear regression model which is linear also in data, and that allows me to estimate all the beta parameters. As an example, let's say I want to explain final with SATM and SATV. I do quick estimate equation, final SATM, got the intercept, like this. But I also want to use the interaction term between SATM and SATV. So I need to then just add SATM times SATV, like this. In Gretel, you would just click the plus sign and create a new variable, which was the product of these three. Estimate it, and I have my B1, my B2, my B3, and my B4. Again, in this particular case, it was not a very good idea. We can see that this new variable that we've added is highly insignificant. So let's look at the point. Why would we add an interaction term like this? Well, the answer comes from looking at the marginal effects. If I want to find the marginal effect of x2, the expected value of y given x with respect to x2, that goes away from this term. I'm going to get beta 2. This term doesn't have any x2 term, but this one does, right there. So the derivative of the last term will be beta 4 times xi3. Well, we've removed the I in the derivative, so I can remove it here as well. So here's the key point. The marginal effect of x2 is now allowed to depend on x3. That is, in economics, often a feature that we would like to have in our model. For example, if you're estimating a demand equation, you may want to allow the marginal effect of price on demand to depend on the income. So the price effect on demand may be different depending on the income of the individual. People with a high income may react to a price change differently from people with a low income. And of course, we can estimate this marginal effect of x2 by simply replacing beta 2 with b2 and beta 4 with b4. In this particular case, if I want to estimate the marginal effect of SATM, I would take this number, and to that I would add this number times the value of the SATV score. You can, of course, allow this marginal effect to depend on both x2 and x3 simply by adding one more term here. I could also add beta for xi2 squared. Then, no, that would be beta 5 in that case. 4 is already taken. So then I would allow the marginal effect to depend on both variables. So to summarize this, we just simply create a new variable, which is the product of these two, and that's called the interactive term or the interaction term. And if you only start with two explanatory variables, there's only one possibility for this one. But if you have more explanatory variable, then you can create interaction terms between any two, so the possible set of interaction terms grows really quickly with more explanatory variables. So by replacing the interactive term with xi4, we have a model that we can estimate using OLS, and in this model we find the marginal effect, and it becomes equal to beta 2 from this term plus beta 4 times x3 from the final term. That is of course unknown to us because the betas are unknown, so we estimate it with b2 plus b4 times x3.